is largest? And that's what we wanted to know. So it's just the direction of the gradient when we fill in a particular point. We get a particular gradient, and that stands for a direction. So the gradient tells us the direction of maximal change. So if we're talking about the error function as the surface, and we want the error to decrease as much as possible, when we make a change, remember these would be the weights. When we make a change in the weights, we want the error to decrease as much as possible. It's the gradient that will tell us what direction to go to make the biggest change. Now, I was a little confused when I was thinking about directions when I first learned this, but the direction is given in the XY plane because once, we're at this point, it means we're up here, right? We can say when X and Y, the inputs are here, then this is where we are. And then we're going to move to some other place on the surface, but really that means in the XY plane, we've moved to somewhere else. So if we want to know where to move, we can say in the XY plane, which direction should we move? Okay, so the directional vector that we're talking about is in only the XY plane, even though the whole curve is in 3 space. Now, if the gradient tells us to move in this direction to get the most change, then actually the direction that we would move to get the least amount of, the direction of steepest descent will be in this direction. So actually, I misspoke just a minute ago. We don't want to move in the direction of the gradient. If we want to decrease the error, we would want to move in the direction of the negative of the gradient, the opposite direction of the gradient. So they say it's minimized when you point in the opposite direction of the gradient. So that is a very powerful answer. Now, I'm not going to go through all of the details here, but they arrive at this statement here, which says that the directional derivative based on a particular u, so in a particular direction u, remember we're located at a point A, we're standing somewhere, in other words, and we call that place A. So the directional derivative, they give this formula. And this is where that result comes from. That is where the result that says we should move in the direction of the gradient comes from. And why is that? This says, given a particular direction u, this is what you're going to get for the directional derivative. But if you look at this part here, this is the magnitude of u. But remember, u, we said it's a unit vector. So the magnitude of a unit vector is just 1, so we can just get rid of this part, and we get this. So this says that the directional derivative for any direction u is just this part. Well, this doesn't even have u in it. So this is like just a constant, doesn't depend on u at all. But this has u in it because this is the angle between u and the gradient. So when is the cosine largest? When the angle is smallest, when the angle is 0. So that means we want the angle between u and the gradient to be 0. That means that u should point in the direction of the gradient. Okay, so it might be useful just to go through some kind of example just to see this. Now, the example is not going to be the kind of example that we're interested in where we're talking about the error function. It's something else. We're going to be talking about pressure function, so air pressure. So whereas in our examples, we had a surface in 3 dimensions, so we had 2 input variables, but here it's a little different. We're going to have the pressure, so the air pressure, so the input variables are x, y, and z. So we're using all 3 dimensions, spatial dimensions for the input variables. So the output variable is not, not sort of uh, visualizable. But nonetheless, we can say we have some output variable. I don't know what to call it since we're using x, y, and z. I guess we could call it u. So that's our output variable. And we have three input variables in this example. And this is the pressure function. And this is on some planet somewhere called Nil-Rabo. And they're saying the distance, the units here are in thousands of kilometers. So as you move, you know, like at 0, 0, 0, maybe maybe it's not air pressure. I'm not sure what it is, some kind of pressure. But maybe it's the pressure, the internal pressure. But anyway, at 0, 0, 0, the pressure is, we put in zeros here, and there's no pressure there. And then as we go to different locations, we change x, y, and z, we get different pressures out of this function. So we can say, okay, at this particular point, what is the pressure? We can just put that into here. We get out some pressure, some number. And then we can say, what's the rate of change of the pressure when we're standing at this point in 3 space and we move in a particular direction in 3 space. So what direction? One in the x direction, one in the y direction, and one in the z direction, or one in the I, k, and j directions. So then we're using the first theorem that we saw, which said that the directional derivative in this direction is going to be the gradient at this point. That's what this says, the gradient at this point, dot u. That's what we said earlier. We said earlier that the directional derivative in a direction v is the gradient dot v. So that's all we're doing. So here, it's the gradient dot u, because we want to go in the direction of u. We want to know the directional derivative there in the direction of u. And so we can just figure this out and dot it with u. And so they do that and they get that. So that is in this direction. But we might also want to know, like, in which direction does the pressure increase most rapidly? And we also had the answer to that. It's in the direction of the derivative. I'm sorry, of the gradient. So here's the gradient at this particular point. So we have this. When we do that, I'm sorry, no, we have, sorry. So they're taking this, which is this, as you can see from this part here, and then they're dividing it by the magnitude of this. So why are they doing that? Why are they dividing it by this? Because they just want to get the direction with it. They want to have the direction as a unit vector. So you don't have to do that, but maybe it's more standard to do that. So this direction is true. This is the direction of greatest ascent, but we can also divide it by a constant. It's still pointing in the same direction. And that's what we're doing here. We're dividing it by a constant. And when we divide it by this particular constant, this is the magnitude of this, then we get a unit vector pointing in the direction of greatest ascent. And then further, they point out that the actual rate of increase in this maximum increase direction is the norm of the gradient. So it's this amount. This is how much increase we're getting as we move in the direction of the gradient. Okay, let's take a look at this question. It says calculate the normal vector to the line there. So this is a line. This is the equation of a line. So I don't know what it looks like, but it looks like something. So it's the equation of a line. So we want to know the normal vector to that line. By the normal vector, we mean the vector which is perpendicular to this line. So of course we know how to do that. One way to do that is to write y equals, solve this for y, then we get the slope, and then we know that we take 1 over the slope and the negative of that, and that's going to give us the slope of the perpendicular line. That's basically what we're trying to do here. But we want to express it differently. We we want to say we want to get the normal vector to this line. And it turns out that all you have to do is take the coefficients of the x and the y, and that will give you the normal vector. So in this case, I mean this here, 3 and 4. So that will be normal to, maybe I shouldn't use that color, so that will be normal to the to this line. It'll be, in other words, it'll be perpendicular to this line. Now, how can we prove that? So what we would need to get a vector which is parallel to our line, and then if we found that vector, then we could take the dot product of that vector with this, and if we get 0, then we've seen that that means that they're perpendicular. So let's see what about that. So how can we start with this line? Let's solve this equation for y. So I hope I've done that correctly here, and you can stop the video and make sure this is correct. So if this is true, then the slope is minus 3/4. So what does that mean? So that means, by the way, I just drew this line in here arbitrarily, so I don't know. This is probably not anywhere near the right line. But anyway, the slope of the line is minus 3/4. Okay, so let's figure out what the slope means here. So it's, if we go over 4, we go down 3. So if we go over 4, we go down 3. So we have that point. So we have that line. By the way, this line, I just drew that arbitrarily, which wasn't terrible, but it wasn't right either. So anyway, this is the line. So what is the vector which is parallel to this line? Well, any vector along here is parallel, and in particular, the vector which goes from here, to this point, is parallel. Another, what vector is that? That's for -3. This is a negative. That's a -3. So it's 4, -3 is the vector. So 4, -3. Okay, so that is the vector which is parallel to this line, and my claim is that when you take that, and if you take the coefficients of these and form a vector which is 3, 4, if you take the 4, -3, and you take the dot product of that with the 3, 4, which I got from here, those two will be perpendicular, so their dot product will be 0. And you can see that that's true because you take 3 times 4 plus 4 times -3, you get 0. So that shows that to get the normal to this line, you can just collect the coefficients and form a vector, 3, 4, 3, 4. Now, do you think that was just a coincidence? No, it's not a coincidence, and it's generally, of course, it's generally true. So we should prove that it's true, but we'll just say that it's probably not a coincidence, and that it is generally true that you can do that to get the normal vector. Okay, so that's very interesting. And also, how about if you have not just a 2D situation like we have here, we have x and y, suppose we have a 3D situation. So this, remember, is a plane. But what does 5, 4, 2 give us? If we form a vector, just like we formed a vector 3, 4, what happens if we form a vector 5, 4, 2? What does that give us in relationship to this plane? Well, it turns out that that's going to be a vector which is normal to the plane. What does that mean, normal to the plane? Well, that's not exactly clear, but it's sort of intuitively clear, right? We can imagine, sort of a vector which is perpendicular to the plane. But really what that means is, or another way to think of that is that that this 5, 4, 2, which comes from here, 5, 4, 2, is perpendicular to any vector that lies in the plane. So if we have any vector in our plane, in this plane, and what can we do? We can take the dot product of, if we know a vector in this plane, we can take the dot product of it with this, and they will be perpendicular, meaning what? That the dot product will be 0. So that's what we mean. But we can just call it normal to the plane. So if we collect these coefficients and form a vector, they will also be, they will form a normal, in this case to the plane. In this case, it was to the line, to the orange line. So we'll call this vector 4, comma, -3, this one here. We're going to call that a direction vector for this line, for this gold line. So this is a direction vector for the gold line. I guess I need to put arrows on there. Okay, I made it a little thinner. So there's that's a direction vector for the gold line. So we'll use that terminology, a direction vector for the gold line. Okay, so next we say, what do we mean by a direction vector for this plane? So as I just said, basically what we mean is any vector which is in the plane will be called a direction vector for the plane. Okay, by direction vector we mean as opposed to the normal vector. So a direction vector is sort of in opposition to or opposed to the normal vector. That's what we mean by the direction vector. So in the plane, it could be any vector in the plane. And on the line, it can be any vector on the line, I guess we could say. So how can we find a direction vector? How can we find a vector in the plane? So you can just pick any 2 points in the plane, in other words, any 2 points that satisfy the equation of this plane, and then subtract their position vectors. So we talked about that before. We have a vector here, a point here. Whoops. So we have a point here and a point here. We can construct the vectors that look like this. That's the position vector for that point. This is the position vector for that point. We can call them OP1 and OP2, or we could call them A and B. And if we subtract A minus B, we'll get C, which is here and goes from B to A, as we've discussed. So, and that's going to be a vector in the plane. So we can just, that's one way to get a vector in the plane. Just choose any 2 points and subtract them, subtract their position vectors, and that will give you a vector in the plane. So we can do that. We can take x equals 0 and y equals 0 and find out what z equals. So we get 0, 0, 5 is 1 point, and then we can take x equals 1 and y equals 0 and solve for z, and we get z equals 5 halves. So another point is here. So we have 2 points in the plane here and here. And then we can subtract their position vectors. P2 minus P1, we call those the position vectors here. I call them A and B. And so if we do that, we get what we call a direction vector. And this is it. If we subtract those 2, that's what we get. So that's an example of a direction vector for this plane. Okay, and then once we have that, our claim was that we can still do this trick of taking the coefficients of the plane, or of the x, y, and z from the plane equation, so 5, 4, 2, and if we dot that with our position vector, or direction vector, sorry, with our direction vector, then that is going to be 0. In other words, that they're going to be perpendicular. In other words, this does give us a normal, doing this 5, 4, 2, does give us a normal vector to the plane. And if you try the dot product of this and this, it does turn out to be 0. And the point here is, I guess, that this is not a coincidence, right? It's very unlikely that, just this is the only time that it's going to work, that when you collect these coefficients, that they're going to give us the normal vector to this plane. So we can prove that it's true, but I just want to show you this as, I think this is sort of makes you believe it without actually proving it. So now we know a way to get the normal vector for a plane, but we don't actually need it for the plane for what we want to do. We just need it for the line. So we just need it for this case. So we have a line, we have the direction vector for a direction vector for the line, and then we collect the coordinates here, and we get a vector, and this vector and the direction vector will be their dot product. Well, those vectors will be normal to each other or perpendicular to each other, and the way we show that is just take their dot product, and it'll be 0.